Dear students, today we shall see the two component system in phase diagrams. Let us take the phase rule, that is F is equal to C minus P plus 2. In that, if you apply the component that is 2, the phase rule becomes 4 minus P. If you apply the minimum condition, that is number of phases equal to 1, in that situation the degrees of freedom becomes 3, which means there are 3 variables you have to describe the system completely. That means you have to draw a 3D graph. Drawing a 3D graph and understanding it is very difficult, and therefore we do one thing. We reduce one component, one variable, that is pressure. How do we reduce? We keep pressure is constant. When pressure is kept constant and that variable is eliminated, and therefore we draw a graph only between temperature and component, which are the composition, which are the two variables, and therefore drawing and understanding the phase diagram becomes easier. Now the phase rule takes a different form because we have eliminated one variable, that is pressure, and therefore only temperature will be there. And take phase rule becomes C minus P plus 1. That's why I represented as F dash. If you apply two components here, and that becomes 3 minus P, F dash, that becomes 3 minus P. And this form of phase rule is known as reduced phase rule, otherwise known as condensed phase rule. Okay. In two component system, we use only the reduced phase rule. That means we will be drawing graph only temperature versus composition. Now let us consider a solid liquid equilibria alone in our examples. Let us consider a solid liquid equilibria. In solid liquid equilibria, there are 3 types of system possible. The one type is called, the two components that we take are not miscible in the solid state but completely miscible in the liquid state, and that mixture is called as eutectic mixture, and that is one type. Example is silver lead system. Another example is potassium iodide and water system. The second type is the two components that we take react themselves and form a stable compound, which means A and B react to form AB, a new compound, with a congruent melting point. We will explain what is congruent melting point when we see the example. The third type is the two components react and form a compound but with incongruent melting point. These are the 3 types of system you get in two component systems. Let us see one by one. First, let us see the simple eutectic system. I am not taking as a general form of simple eutectic system. Straight away I take a lead silver system and I explain how a simple eutectic system works. And this is the phase diagram of lead silver system. To understand this, the diagram, we take composition in x-axis and temperature in y-axis. Okay, as we have told already, two component system, we take only two variables, that is temperature versus composition, and pressure is kept constant, and therefore we draw this diagram versus temperature and composition. Okay, that you have to understand. And this is the point. Let us consider the point here where lead in x-axis, where lead is 100%, and in this area the lead is 100%. If you take in this area, maybe a silver is added, lead and silver, where lead will be more and silver is less. If you take any point here, that means the silver is more here, maybe 90% and 10% lead. This is how you have to understand. but at this point silver is 100%. Along this axis silver is a 100%. Okay, you have understood that. Now here what we study, the temperature we study is the melting point. The temperature that we study is the melting point here. Now let us start. Take pure silver, 100% pure silver. The pure silver melts at 327 degree Celsius. That is, the melting point of pure lead is 327 degree Celsius, or we can also call it as a freezing point. The freezing point of lead is 327 degree Celsius, and that is represented by the point A. What happens when silver is added to lead? That means at this point, that means now the lead is not 100%. We have added some silver to that. That means let us consider lead is 99.5%. Silver is 0.5%. That means I have added a small amount of silver to lead. Now what will be the melting point? You can observe that here the melting point now is below 327. That means melting point is lowered when silver is added to lead. Yeah, and this happens. If you add more silver and the melting point is lowered. If you add more silver, okay, it goes until point C. Until point C, this trend follows. On the other hand, if you take pure silver, that is 100% silver, if you melt the silver will melt at 961 degrees Celsius. 961 degrees Celsius, that is the melting point, or you can call it as a freezing point, both are same. When you add lead to the silver, that means you take this point, that means for example it is 90% silver and 10% lead you have added. You can also see here the melting point of silver also lowered. If you add more lead, the melting point of silver lowered. It continues in the similar fashion until the point C, and therefore this curve is known as the freezing point curve of silver, and this curve is known as the freezing point curve of lead. Okay, this is what happens, and you can see these two curves exactly meet at a point C. At a point C, and this point is known as a eutectic point, and that happens at 303 degrees Celsius. That is the eutectic temperature of a lead silver system. For other system it may be different. For lead silver system it is 303 degrees Celsius. And the composition at the point C is 2.6% of silver and the remaining will be lead, that is 97.4% lead. And that mixture actually melts at 303 degrees Celsius. And this point is very important. Why it is important? That means below this temperature, whatever the composition, the mixture remains in solid state. Below this temperature, whatever may be the composition, the mixture will always exist in a solid state. That means this is the minimum melting point or EC melting point. But EC melting composition is this. If you take any other composition, that will be, the melting point will be higher. And this is the lowest melting point, EC melting, and the EC melting is represented as eutectic. That is called eutectic composition. The eutectic temperature is 303 and eutectic composition is 2.6% of lead. Now let us explain the diagram. Okay, the whole diagram, the curves and points, all those things. We have already seen what is the point A and what is point C and what is point B. We also explained the curve AC, the curve BC. Now let us explain the area here. As we have seen, in this area, the mixture will exist in liquid state, homogeneous liquid state, miscible. Let us consider any point in this area. In this area, there will be liquid melt and solid silver. And in this area, there will be liquid melt and solid lead. And below the eutectic point, everything exists in the form of solid, but here there will be solid silver and eutectic mixture. And in this area, there will be solid lead and eutectic mixture. And what will be in this area? You will get only eutectic mixture. This is the importance of this diagram. Let us calculate the degrees of freedom for all those things. And therefore, in this along the curve AC, let me explain the degrees of freedom in along the curves. Along the curve AC, that means the liquid melt and solid lead is the phase here, and here it is liquid melt. The liquid melt and this phase will be in equilibrium. Along the curve BC, this phase and this phase will be in equilibrium. Okay, there are two phases in equilibrium. What about the point C? At the point C, the liquid melt and the liquid solid silver and solid lead, all the three phases will be in equilibrium. That is how you have to understand. If you calculate degrees of freedom, here in this area, there is only one phase, and therefore 3 minus P, that will be 2, and therefore the degrees of freedom in this area will be 2. That means bivariant. You have to represent both the composition and temperature to describe any point in this area. That's why we call it as a bivariant. If you calculate any point along the curve, any curve, this curve or the curve BC or curve AC, any point you take, that means here if you apply phase rule, that is f dash equal to 3 minus P, there are two phases, this phase and this phase coexist in equilibrium, and therefore 3 minus 2, that becomes 1, and therefore degrees of freedom in this curve are either this curve or this curve is 1, that is monovariant, which means if I say the composition, automatically the temperature is fixed, or if you say the temperature, automatically the composition is fixed, and therefore it is enough to say only one variable. That's why along the curve the degrees of freedom is 1, and that is monovariant. Okay, because there are different point in the curve, and you have to say one variable to describe which point. Okay, but eutectic point, if you come to eutectic point, the degrees of freedom, here there are three phases, the liquid phase, solid lead and solid silver, all three coexist, and if you apply F is equal to 3 minus 3, f dash equal to 3 minus 3, that is equal to 0. That means the degrees of freedom is 0. That means you need not describe any point, because eutectic point is only 1. That means both the 303 and 2.6 is fixed, it does not change, and therefore you need not describe using any other variable. There is no variable, it is fixed. Composition is fixed and temperature is fixed. and that's why it is called more invariant. Okay, it is only one point, and that point is always 3.303, and the composition is always 2.6. You cannot change that. That's what we called as a invariant, and this is about the degrees of freedom here. And what I have explained is I have returned here. Just I will go through first. The lead and silver are completely miscible in the liquid state. Pure lead melts at 327 degrees Celsius. We have seen that. When silver is added, the melting point lower, and along that is called a freezing point curve. Similarly, pure silver melts at 961 degrees Celsius. Addition of lead lowers melting point along BC, and the BC is called a freezing point curve of AC. Along AC, there is lead, pure lead, and liquid melt is in equilibrium. Along the curve BC, pure silver and liquid melt are in equilibrium. The curve AC and BC meet at a point C, and that point we call it as eutectic point, where silver, solid lead, liquid melt, all the three phases coexist, and the temperature is at 303 degrees Celsius. The eutectic temperature is 303 degrees Celsius. Eutectic composition is 2.6% silver and 97.4% lead. We have calculated degrees of freedom in all the areas below and above the curves, and that is 2. There is only one phase exists in all the area, and there are 3 minus 1, which is known as bivariant. In all the along the area, there are two phases which coexist, and if you apply that 3 minus 2, that is 1, that means monovariant. And at the point C, which is eutectic point, if you calculate degrees of freedom, there are three phases that coexist, and 3 minus 3 equal to 0, that is invariant. We have seen all this. We have explained the phase diagram. Now we are going to see an important phenomena in the simple eutectic system, that is desilverization of lead. For lead silver system, it is called desilverization, but other system it may be called in a different name, but this phenomenon will happen in all the simple eutectic system. Let us consider a composition, a system where lead is 99% and silver is 1%, and this mixture is well heated above the melting point. You know, the melting point is 371. I am taking this mixture, I am heating this mixture above 371 degrees Celsius. What will happen? It will make a liquid melt. Now what I will do, let us consider this the point. This is 371. I am heating, and this is the composition where the silver is 1% and lead is 99%. The point A. What I am doing, from the point I am cooling the mixture, cooling until it reaches point B, until it reaches the point B. What will happen at this point? You can see what actually happens. It is a mixture of silver and lead. When it reaches this mixture reaches this point, that means below 371, some temperature, consider maybe 369 something, you consider. If that temperature is reached, what will happen? Lead will start to crystallize. Lead in the mixture, there are lead around 97%. Some of the lead will be precipitated, not all the leads, but some of the lead will get precipitated here. Okay, when some of the lead is precipitated, the composition of the liquid melt will change, because we have taken 97.4% of lead and 99% of lead and 1% of silver. What will happen? For example, 1% or not 1% or 0.5% of lead get deposited. Now, the composition of the lead changes in the liquid melt. Okay, now the lead, some amount of lead is deposited. It is not now the original 99% and 1%. There will be decrease in the percentage of lead and therefore increase in the percentage of silver. I don't know whether you have understood or not. Let me explain with example. Let me take 99 gram of lead. I am taking 99 gram of lead and 1 gram of silver. 1 gram of silver. Okay. Now, since it is total is 100, total is 100, I am saying this is 99% and this is 1%. 99 gram becomes 99%. 1 gram becomes 1% because it is 100. Now, what happens? Now, what happens when lead is get precipitated at this point? When lead is get precipitated at this point, let me take that 1 gram is precipitated. For example, 1 gram is precipitated. What will be the remaining grams? What will be the remaining? The remaining will be 98 gram. Remaining will be 98 gram. And this is the new percentage. This is the new percentage, new weight of lead. Now silver is not precipitated and therefore it will be 1 gram. Okay. Now the total becomes only 99 gram. Okay. Since 1 gram of lead is becoming solid, in liquid melt the total now will be 99. If you consider 99, total 99, 98 in total 99. If you calculate the percentage, that means 98 divided by 99 into 100 multiplied by 100. If you do that calculation, that is you can make that calculation 98 divided by 99. That equals 98.9%. That is now it is a 98 percentage wise it is a 98.9%. What happens actually? Similarly, if you calculate the percentage of silver, that is 1 divided by 99. Now it is 1.01%. Okay, you can see 1.01%. Okay, if you see now, what happens actually, the lead from 99 it decreased to 98.9%, but the silver percentage, it remains as 1 gram, but the percentage increases in the liquid melt. When it happens, at this point, when lead is precipitated, the composition automatically changes to this place. Now, this place. Now what you have to do? I am further cooling the mixture. If I further cooling the mixture, at this point some lead will get deposited. Now the lead will lose the liquid melt will lose the percentage of lead and the percentage of silver increases to this point. I am again lowering the temperature. When reaches this point, and some more lead will be deposited, and this process continues, this process continues. But at this point, what happens? When it reaches the point C, okay, if you repeatedly do this, actually the composition exactly moves on the curve AC, and lead is getting deposited. A pure lead is get deposited, and the liquid in the solid, there is a solid getting deposited, that will be pure lead, and in the liquid melt it is silver and lead, where the concentration of silver is keep on increasing and the concentration of lead is keep on decreasing, and this happens until the system reaches the point C. At this point, when it reaches this point, if I lower the temperature further, all the liquid will become solid. All the liquid, there won't be any more liquid melt. Suddenly all the melt will become solid. Already we have pure lead deposited. Now the liquid, that is silver and lead, the eutectic mixture, get deposited as solid, not separately as silver and lead. Okay. Now the situation will be like this. There will be a pure lead in the solid in some part that is previously deposited here, and that will be present in the mixture. When it reaches this point, since the concentration changing, when reaches this point, that is 2.6%, and this, okay, when it reaches 2.6%, what will happen? Suddenly all the melt will become solid. In that solid, it is a mixture of solid, not pure lead or not pure silver. The same thing happens here. If you take silver, more silver, take at the point A dash. Okay, I am take example 80% silver, okay, 80% silver and 20% lead. I am taking that mixture and heating up to this temperature at point A dash, and I am cooling. It will be in liquid state. When I reach this point B dash, what will happen? Silver will get deposited here. Here we get lead deposited, but what will happen here? Silver will get deposit, and silver, some of the, from the mixture, some of the silver will get deposited. Now when silver is gets deposited, what will happen to the mixture composition? In the liquid melt, the silver composition will get decreased and the lead composition will increase, and therefore the system will change to this point. Okay. Now when I further cool the liquid melt, it will cool. When it reaches this temperature, again silver will get deposited. Since silver is deposited, the composition will change and it will go there. Again if I cool, it will reach here and silver will get deposited. Pure silver will get deposited. The composition of the liquid melt will change. When I reach this temperature, this composition, that is 2.6, I am cooling. When I reach this point C, suddenly all the liquid melt will become solid. In all this area, there is only pure silver is getting deposited and the liquid melt is there, that mixture is there. But when it reaches this point, all of them, if you do this, if you take 80% of silver, 20% of lead, if you try to cool step by step, what will happen? Initially silver will get deposited, pure silver, and when it reaches this composition, eutectic composition, suddenly all the eutectic mixture will become solid, and that eutectic mixture we call it as a alloy. Okay, this is what. And if you take this composition, pure silver is deposited, and this is called as a desilverization. Or here uh, we lead is get deposited in this area, and this process is called as a desilverization that I have explained here. Okay, we can see here the mixture is well heated. I am taking a composition well heated above. Okay, I have explained all this. What have we explained? I written here. From A to B, when the point B is reached, when you cool, when the point is B reached, lead will crystallize out as a solid. As a result, new concentration of lead. Now the concentration of lead decrease and the concentration of lead silver increase, that I have already told you. Further cooling, more lead will get crystallized, and the system will shift to higher concentration of silver, and this phenomena continues till the eutectic point C, that is 2.6% of silver. Similarly, okay, this I have explained clearly, and this is what called desilverization of lead, and this is an important phenomena in a simple eutectic system. Okay, now let us see potassium iodide and water system. The same thing, only the temperatures and the eutectic composition, eutectic point is different, otherwise the same system is. This is also simple eutectic mixture. Lead, the potassium iodide water system also a simple eutectic system in which the pure ice, water will be exist in ice state. That's why the pure water melts at 0 degrees Celsius and become ice. As we have seen in lead silver system. Okay, when you add addition of potassium iodide to ice, what will happen? It will lower the melting point along the curve AC, the same thing. And this is freezing point curve of ice. Similarly, here there is one change apart from lead silver system. We have seen that silver melts at 971 degree there, but here there is a problem. You cannot identify the melting, we cannot represent the melting point of Ki, because the melting point of Ki is so high, very high, that is you know how much it is high. It is above the critical temperature of water. That means if you heat pure Ki to that, in that temperature water does not exist, it will decompose. That's why we don't represent the pure melting point of Ki here. We do not represent here because it is very high and it is not relevant to use it here. And therefore, we take a point B where it is not pure Ki, the temperature that water can withstand. And we start from there. And therefore, in this area, if you take any point here, the water cannot exist there, and therefore we cannot study such kind of system. That's why we don't take. We start where water can exist, the temperature and melting point. And in that case, I am taking Ki here and I am cooling. And this is the, when I add water to that, more water, the melting point also decreases. The temperature at which becomes solid Okay, the melting point or freezing point decreases, decreases, decreases. Okay, and this is the freezing point curve of a Ki solution, water, Ki water solution. Okay, the similar way, if a water melts at 0 degree Celsius and the similar eutectic diagram we get, this is AC is the freezing point curve of ice, and this is freezing point curve of Ki, and this is a eutectic mixture. We have already understood by lead silver system the same thing, and if you say the temperature, that is enough, you can understand. The eutectic composition in this system is minus 23 degree Celsius, and the eutectic temperature. The eutectic composition is 52% of Ki and therefore 48% of water. That composition is the eutectic composition. The similar thing happens there. We have seen desilverization. If you take point A here and take this composition, that is maybe 40% of Ki, 60% of water. If you take and I am heating that to the up to this temperature and cooling, when this temperature reaches, what will crystallize out? Ice will crystallize out. Okay, when ice is crystallized out, the composition of water decrease and the composition of Ki increase, and it will reach this point. And when I cool, and after reaching this point, what will happen? Ice will separate out. Since ice is separated out, the composition will change to this point. Now I am again cooling. When I reach this point, ice will separate out. Okay, and the composition changes. And further cooling. Okay, and I am reaching this point, that is the eutectic point. After this point, if I cool further, it will go and suddenly all of them get precipitated. Okay, this is what we have explained in lead silver system. The similar thing happens here. If you take a composition here, maybe 60% of Ki and 40% of water, I am heating that to up to this point A dash, and I am cooling that mixture. It will cool up to this point B. When the point B reaches, what will happen? Potassium iodide will get precipitated. And therefore the composition of potassium iodide will decrease and the lead water will increase, and therefore this will shift, system will shift here. Now I am further cooling. When it reaches this point, Ki will get deposited. Since Ki is deposited, the solution, the concentration in the solution of Ki will decrease, the water concentration will increase. Similar thing happens, and Ki, okay, until it reaches this point. When this composition is arrived, I am cooling until this point. When it reaches this point, both that solution becomes solid. Ice and Ki mixture will get solidified. Okay, this is the water and Ki system. This is simple like lead silver system, except we don't represent the boiling point of Ki here, because it is above the critical temperature of water, and other changes are only the temperatures, this temperature and this composition. Otherwise it is a simple eutectic system, just like lead silver system. That is what I have written here, all of them. We have calculated degrees of freedom in along the curve BC1. Okay, along the curve BC it is we have already seen. Along the curve AC, ice and solution are in equilibrium. Along the curve BC, Ki and solution is in equilibrium where the degrees of freedom is 1, and eutectic point Ki, solution and ice all are in equilibrium, and the degrees of freedom is 0. That means it is invariant. Okay. And this is the eutectic temperature minus 20 degrees Celsius, and this is the eutectic composition of a Ki water system. Okay, I have explained that crystallization of ice and crystallization of Ki. Okay, let us meet in another video. Thank you.